nematic colloids, so water-rich materials. Then I will speak about what is binding nematic colloids and how strong it is binding. And I will not skip methods of assembly or manipulation, which is optical tweezers manipulation. I will show you that this is quite different in liquid crystals than in isotropic fluids. And then we go to the subject. So this is the different kinds of assemblies. I will classify them in several classes, like assembly by localized defects. You will see chains and two-dimensional colloidal crystals. Then I will move to more exotic assembly. You will see that we can wire up colloidal particles by entangled defect lines into different superstructures. And even more exotic physics could be found in chiral nematics. And at the end I will just show an example of application. This is the electric field effects on the structures. So the nematic colloids are the dispersions of particles in liquid crystals, in nematic liquid crystals. So these particles could be solid or liquid particles. And in 74, you will find in the book by Dejean in 74, you will find the talking by Piransky when they decorated the surface of a nematic liquid crystal by bubbles, air bubbles. And you can see that these air bubbles self-organize into chains following the director as a surface. And this was later revived by the Poulin and the Stark events in White in the famous paper in Science, when they make mixtures of water droplets. So you take water, you take the nematic liquid crystal, and you take surfactant, you mix that, and you see that some kind of chains are formed. So these are chains of water droplets. And you are asking yourself, why do they not coalesce, right? And this is this was answered by this group in this video. So why they do not coalesce and what stabilizes them. And they were the first to show that it's very important the role of the topological charge and topology. So let me just go to the topological charge and the concept of the topological charge. So a nematic liquid crystal is uniform. So I will just draw uniform lines representing its stable state. So all the molecules are lined from these lines in the vector. And then you take a good particle, it could be microsphere or something like that, which imposes, let's say, homotropic surface condition. And for a liquid crystal, and when you put this inside a liquid crystal, there's obviously a frustration. And this frustration, because of the surface condition, the cut surface, and the homogeneous medium, generates topological defects. And these defects appear in a form of small loops and points, singular points. And this is a list of course, not complete or reference in the subject. How do they look like? So if you take the microsphere and put it in a nematic liquid crystal, and this is, let's say, homotropic surface anchoring on the sphere, you see that it's not a sphere, but it has a small defect. So this is the defect which evolves naturally because of the conservation of topological charge. And if you would draw the director field lines, you see something like this. So this goes into the particle, preserving homotropic condition, but there is a singular point. So it's they call it hyperbolic Hedgehog defect. This is a defect where the field lines avoid this point. And inside this defect, the order is reduced. That's why this scatters light, because the refractive index is different at this point, and is easily observed. You can see that this has a symmetry of a dipole, and by choosing a different surface condition, you can change this dipole into the so-called quadrupole, and you can think of as taking a point and then stretching it, forming a line defect circle, which is in this language is called the subtororing. So you have a sphere which is encircled by a singular point of a singular ring. And there's an interesting aspect, because you see here that the particle not only is not spherical symmetric, but appears much larger because of the elastic deformation which it carries around. So this is a detailed view of this hyperbolic defect. So you can think as a one point defect, and the other point defect of another kind is hidden here inside the colloidal. So this one is called the radial catchpole, and this is the hyperbolic catchpole, and this is a paper which discusses in detail all these kind of defects. So it was shown in 90s that these topological charges behave, and the topological dipoles and quadrupoles behave very much like the electric charges and the series of electric charges. So you can think of analogy to the electric dipoles having plus and minus, but of course these are not plus and minus in the sense of electric charge, but of the topological charge. And in a uniform electric field, this will attract, there will be repulsion. If you place them side by side, this will be repulsed, and if you switch the direction of one dipole, this will be an attraction. And you can actually see that. So here you see two dipoles, topological dipoles, which have their dipoles aligned in the same direction, and they attract. You see that they attract at a very large separation. So this is one of the consequences of this large distortion which is created by the particle around. And using laser tweezers, so these red crosses are just markers for the laser tweezers which we use to manipulate particles. If you bring them together and they are unhappy because they have anti-parallel dipoles, you see first there is a repulsion, and then they will make a way around to find the minimum. This will slowly because the forces are small, and they will form the anti-parallel pair in a stable situation. So you see that these topological defects and the elastic deformation generate forces between particles, and this can be explained in a very simple way. So if you take one particle, this has elastic deformation around it, and then if you take a second one, it also has. Now if you change the separation, the energy of the system will change, right? Because you have gradients of the order. And this is by definition generating the force. It may be attractive, it may be repulsive, depending on the details of the arrangements. How do we measure this interaction? This was already shown in several presentations, but let me just show you that we take video frames of this, let's say these are video frames of these two events that I have shown, and then you determine the positions of the particle at each time. So this can be made very accurately with a typical accuracy of the positions around 2 nanometers, and then you calculate the trajectory as a function of time, and then numerically you calculate the velocity, and then of course you write the Newton law for the movement of this particle. So here you have a drag force, and you have the external force which acts on the particle, and the sum is practically zero, so the resulting acceleration is very small. And from here you can determine, so you know this, you know also this in a separate experiment. You measure particle force on the particle as a function of separation, and then you determine the interaction potential. These interaction potentials for microparticles are incredibly strong because of the large deformation and of the nature of the interaction. So this is the same analysis. You see that the range of interaction is tens of microns, and the potential is very deep. We measured in thousands of kVt, so kVt is the thermal energy available, and you can see that indeed this is much stronger than, let's say, water-based colloids. So for comparison, I draw here the van der Waals interaction, which is responsible for the water colloidal interaction, and you can see that these interactions are way smaller compared to liquid crystal interactions, and also the range is much smaller. So how do we manipulate these colloidal particles? There was already talks about this. So we use laser tweezers and pneumatics. The principle was shown by Ashton already in the 70s. But in liquid crystals we find many surprises. It's much more complicated than in normal liquids because of the complex structure of the liquid crystal. And there's a list of, by no means complete list of experiments dealing with laser tweezer experiments in liquid colloids. And you can divide it into different classes. So this, the first class is when the index of colloid is larger than the medium, than the liquid crystal, then you apply just the usual laser trapping interpretation. You have seen it in the presentation of Kishan. So basically you follow the refraction, because this is larger the index, this is smaller, the change, the direction of light is changed, the momentum is changed, and there are forces exerted on the bead. It has a larger refractive index, forcing it into the center. Now, there is also forbidden trapping, and that's how all the story actually started. You also see, if you take a lower index colloid, that these are trapped. So you ask yourself why. And this is an example of a silica colloid. So it has a refractive index of 1.37 in the liquid crystal, which has a larger index of refraction. And here there's a waste of the laser beam. It's not visible, of course, but you can see it's trapped from a very, very low distance, which is very unusual, because trapping in isotropic liquids is of a certain range. So you explain it by polarization property. So if you look at the liquid crystal around the colloid, then of course the alignment is anisotropic, and for a certain polarization you see that there are two positions where the electric energy is maximized. So these will be favorable positions for trapping. So it's at the edge, not at the center of the colloid. And you actually see it in the experiments. The trap is always at the edge when it takes lower index. Now, if you increase the laser power, the trap becomes visible, just because the nematic is distorted. You go above the Friedrich condition, and you can see again a very strong trapping. And this you can explain also very simple way. So the waves used by Stork deforms the liquid crystal in a ways, and then you can consider this as a kind of object, a virtual colloid or whatever, which then interacts with your real colloids, and that's how you generate trapping, and you can manipulate practically anything in the liquid crystal. So these are just two examples of manipulation. So here I have a dipolar nematic. Yeah. So this is a trap. You see, you can grab it by the edge and you can move it arbitrarily. You can also change the direction of the dipole and so on. And this is another example. So this is the Saturn ring. You can see it, the ring. Yeah, you stretch it and you pull it just by and it would have an elastic force, and you can pull everything practically nematic. So if I first describe what's the assembly when you have this point or small loop defects, you can first form chains. This was shown already a long time ago by Poland and Weitz and co-workers. Yeah, so from pairs you can also form many chains of many particles. Yeah. And you can also form two-dimensional structures. So in this case, you can see when you have a small crystalline here, then this one is repelled, and this one is attracted. And you can see actually that this is can be explained by electrostatics. If you look at the dipole, here this dipolar chains points up, and this also points up, so there's a repulsion. And on this side, this has been switched down, and there is a attraction between these two objects. So it's also can be explained by simple electrostatic analogy. So you can build dipolar crystals. So you can see these chains, they're all dipoles pointing up, down, alternating in position, and so on. This is of course time consuming, but it shows you the principle of assembly of nematic dipolar crystals. And these structures are very robust. So when you assemble this, then you can take the laser tweezers. You can also increase the laser tweezer power above the threshold for the isotropic nematic disposition. So you create actually here a isotropic phase, which is surrounded by a boundary to the nematic. And this can be considered as a colloid, which has gradients all around, so you can drag also the structure as a whole. Yeah. So slowly you can move it, showing it's very robust. Okay, so this is just an overview of structures which could be constructed from a point for the singular defects. So these are quadrupolar chains which are always thin, straight dipolar chains, and two-dimensional quadrupolar crystals and two-dimensional dipolar crystals. Like you can find all details in these papers. If you mix dipoles and quadrupoles, you get a lot of new structures. So this is just our recent publication. You can see so here you have dipoles, we have quadrupoles, and these are chains of dipoles, and these are chains of quadrupoles, and this is an alternating chain of dipole, alternating chain of quadrupole, and so on. And so this is the first example, the second example, and there's a large variety of other structures which have not been classified yet. But you can see from this list that indeed in this mixed crystals you have a lot of new structures and interactions and so on. Now, if I move on to the more exotic mechanism of colloidal assembly, we call it entangled topological defects binding. This work was stimulated basically by the theory. So we have a strong collaboration with the theoretical group, and they have predicted that colloids should be bound not only by sharing these elastic regions of distortion, but there should be also singular lines which are encircling colloids, and we call them entangled colloidal lines. And this is exactly the Landau-Lejeune simulation by Miha Rauning, showing that what happens when you quench a colloidal pair from the isotropic phase. So you have a pair of colloids, you have isotropic liquid crystal, and then you quench it, you cool it very rapidly. So what you see, these lines are lines of constant order. Yeah? So the order outside is large because you have a nematic phase, and then you have tiny lines, singular defect lines, where the order is smaller, lower, and this just entangle the two colloidal particles and bind them into a pair. Now the question was how to obtain these lines and defect units. If you follow the idea, you have to quench it. So this is an example of a quench of a small area around the colloidal crystals. You just increase the laser power, that this is all isotropic, and then you switch it off. You can see that many loops are created. If you look at this loop, this will annihilate to zero, and this loop will remain as a Southern ring. So this is a way to produce entangled states. So if you take two colloids, you can see this tangle, dense tangle, which just clears out, and then you find the stable state. And this is a remarkable agreement with the theory. So we call it figure of 8 because if you look at this line just makes 8. So it's like an elastic rope binding two colloids. There are other states, and you can also do the statistics to determine what is the probability of finding these states. So you can clearly see this one is different because it doesn't make 8. If you look at it from the side, it makes an omega. And this is the structure which is simulated. This is a remarkable agreement with the experiment. And the third structure evolves from this omega. You see this loop which is in between becomes unstable and pushes the two particles away and then condenses in a single point defect. It's running. So you can see there are always two loops, two particles, two loops, right? So it's a signature of the topological charge, and this is simulation. So you can make many, of course, wires from this using these methods. So this is an example of colloidal wire made of figure of 8 entangled defects. Here you can see how it looks when you stretch it, right? You use two laser beams and you pick the colloids and you stretch them. It's like a harmonica, and then it's elastically bound and it goes back. This shows this movie pair. So I will switch on the laser tweezers. Yeah, and this is a real-time image. You can see these forces are rather small, but this entangled loop indeed works as a spring pushing these two particles together. So the question is, why was not this observed before? There were many conjectures whether this does exist or not, but you can see that you really have two ingredients in this experiment. The first one is the conservation of the topological charge, which provides defects. And the second, very important thing, that you must have a symmetry breaking. You must go to the disordered phase and then quench everything down. And during this procedure, you generate a lot of defects, and some of them are just caught by the colloids, and then you get entangled states in the entanglement. And you see practically no spontaneous entanglement if you don't do the phase transition. That means that there is a large energy barrier between these states which are bound by the point defects and entangled defects. So if we go on and if we look at these loops which are developing around the particles, and then you come to the idea what happened. This loop is a kind of singular object which is either isotropic in the core, nearly isotropical, it has very small order. If I take another object, very small, which also generates a lot of deformation, now it will be reasonable to suspect this will be trapped into the loop, because this will reduce the total energy. So if you take a mixture of small and large colloids, and this is an example, so you have here a large colloid, which is encircled by the Saturn ring, running in the plane of this table, and then you take a small one here, and you see that this one is indeed attracted into the ring. You see that it doesn't go radially, but it follows a curved path, so there is indeed could be explained also by the theory, and this mechanism have also been observed in the paper by the group of Garan and predicted by the group of Cleaver. So if you look at the energy of a trapping of, let's say, a microparticle into the ring around such a larger particle, then you again find similar energies, several thousands of keV. And then you ask yourself, what are the smallest particles which could be trapped into these lines, right? Then you can arrive at the calculation. It can be shown that under the red theory works very well down practically to the nanoscale. And this is the results of the calculation. So this is the diameter of a small colloidal particle, and this is the binding energy, right? So you see that, of course, the scales increases with the diameter, and then if the diameter goes to 0, also the binding goes to 0. But you can see that here there is an extremely strong binding already for several tens of nanometers large particles, which means that small particles could indeed be trapped into the rings. And these are examples of the structures which you can either build or even self-assemble, spontaneously assemble. So you can take two colloids and you have a figure of 8. You can fit it with the smaller colloids. And this is just showing that these are colloids indeed are inside the ring, because by changing the focus you can follow all these different particles inside the ring. And this is spontaneously assembled a structure very similar to this one, which was directed. And this is a single Saturn showing it's filled with the small particles. And these are the simulations. So the interesting part here is that is the question whether you could use these rings as a part of the metamaterials. You will hear in the lectures to come that for metamaterials you need a negative dielectric and negative B response, magnetic response. And one of the ways to make a negative response, magnetic response, is to make a very simple LC circuit, right? You take the capacitor, you take the inductor, and then this provides you negative B material. This is known, and it has been extensively studied and already done for a range of frequencies. But here there's a possibility of assembling such a material. So if you take, let's say, conductive small particles, and they will spontaneously assemble into such rings. So what is the equivalent circuitry? So you have this particles is separated from the neighboring particles, so it's like a capacitor, right? And you have also small inductance, because when the current flows, right, you have inductance. So this could be a kind of distributed negative B material, which has already, which of course has to be proved. But this is a photo showing that indeed nanoparticles which are fluorescently labeled are actually bought into the rings. Now I have told you that colloids are even more exotic in chiral nematics. So for a very simple approximation, you take, instead of a planar cell which we were using, you take a twisted cell, twisted nematic cell, and then you find many new structures which you can classify into three classes of stable structures which are observed. So the first one is just ordinary structures. So these are dipoles, quadrupoles, which are bound by singular defects, by points and loops. There's a class of entangled structure, as in a planar cell, but there is a new class which you cannot see in planar cells, which is characteristic for the twisted case, and these are, we call them the structures or the pairs which are bound not by singular but by non-singular director field. This was first observed by Boulain in 1997. And then the structure was proposed by Lubensky in 1998, and this has been calculated recently by Fukuda and Yokoyama, showing that instead, when you have a defect, this defect can escape. Perhaps you know the similar very long problem in cylindrical capillaries, when the defect can escape, and then you have the non-singular escape geometry. And so the same case is observed here. So these are these non-singular bound pairs in twisted nematic cells. So you simply take two perpendicular rubbing directions, and then you find that spontaneously these pairs appear. There are two pairs, two kind of pairs, depending on different from the way that this escape geometry is evolved inside. So you can think of this structure in between as a kind of toroid which circulates around, loosely speaking, and binds these two colloids. So this is something which you cannot observe in planar cells. And these objects spontaneously assemble. So this is just a time series of the movies showing that these pairs spontaneously assemble, and they give a spontaneous form, which are beautiful two-dimensional crystals, which are another class of crystals, colloidal crystals in nematics. And there's a final surprise in this chiral system, which is characteristic by the fact that you have many colloids which are bound by a single disclination line in two dimension. So if I show you the examples, so this is two colloids. You can see there is a line encircling both colloids. If you take three colloids, now you can't see it very well here, but there is a single line. So like this, and this, like this, and this. If you take four colloids, you find the state when you have two lines. One is running like this, and the other is running like that. If you take five colloids, you can see there's a single line weaving and running around these colloidal particles and binding them in two-dimensional assembly, and this goes on and on. So this is something new, which you cannot see in ordinary liquids. You see only in chiral nematics, a simple case of a twisted nematic, and we call them colloidal braids or knots. So if you look at the mathematic theory of knots, you will find exactly the same figures as I have shown you here. Now we don't understand this completely, far from completely, I must say, but I wanted to show it because this is, I think, nice. Now, an example of application. Now, as these colloidal crystals are, of course, assembled by soft matter, and the soft matter is known to have large response to electric fields, then you ask yourself what happens if you take a colloidal crystal and then you put an electric field. So this is just a simple cell, planar cell. The field is applied in a vertical, so perpendicular to the plane of this screen. And oops, you see that this shrinks. It shrinks very much. And this is a laser light diffraction pattern showing that this change, the separation changes for nearly 20%. Now the response time is very slow. It's of the order of 5 seconds or so. Why? Yeah, just because when you squeeze this together, liquid crystals has to flow away, and it can go only through these small voids which are in between the colloids, and this makes the tunable diffraction grating inherently slow, but it has a very large dynamic change. So let me conclude with just a comparison of classical colloids and the nematic colloids. So if you consider, let's say, water-based colloids as a system where the interactions are mediated between the colloidal particles by the electromagnetic field, right? Then you simply take, instead of this field, you take a more complex field, which is in our case the nematic orientational field. This is much more complex because it's a tensorial field, right? And you see that this gives you an incredible new variety of new structures, new phenomena, and so on, which you cannot observe in ordinary liquids like water-based colloids. And we have identified several types of binding mechanism. We try to classify them. So one class would be localized singularities. These are points and loops. The other one would be entangled singularities. So these are still singular line by entangled. And the third class is binding by escape geometry. And each of them generates structures which are 1 or 2 dimensional, and most likely this one should go to 3 dimension. They are all characteristic by very high binding energy, so you measure energy in thousands or even 10,000s of kBt, and you saw that you can make very interesting microstructures which could be possibly interesting for optical applications, and possibly could be tuned by electric field and so on. But that has to be, of course, proved. And of course, this work in this work there's a large group involved. So this is my group, and this is the group of Professor Gruber at the university, the reticle group giving us very strong support. And this is the laser tweezers group, which made a very good acoustic deflector setup. And this is the group from Institute of Physics here, which also helped a lot in our research. Thank you very much for your attention.
Questions?
For your isotropic loops, did you look at the line tension? I mean, did you measure the line tension and the dynamics of the shrinking?
Yeah, this line tension measurements was done by Ivan. Who is here? We didn't do that, but there's work on line tension measurements. Yeah.
So in the two-dimensional crystals, is the planar nature coming because it's just tightly confined by the cell?
Yeah, it's confined by the cell.
So if you have a nematic in the bulk, what would happen?
Yeah, well, we have to organize the assembly somehow, right? Because if you just, well, there are also, there's a recent work by the Korean group, and they put everything in the sack, like, and they put this sack in a water. So this by surface tension, this compresses it and makes a nice two-dimensional structures done by this very clever experiment. But we are thinking of doing this systematically, which means that we must somehow first make a two-dimensional layer, then transport it and put another layer on top of it, and so on. But that implies microfluidics.
Time for a couple more questions. Matt? Yeah?
I'm not sure if I catch how the liquid crystal is aligned and boundary.
It's planar, homogeneous. I showed you that it's homogeneous alignment, right? Planar, always planar. Yeah.
So the liquid crystal aligned parallel with
Right. Yeah. But you cannot do that because the basic forces are provided by a nematic, right? So if you heat this up, it's going to just explode and diffuse away. So this is stable only in the nematic. Yeah? Because the basic forces, interaction forces, are provided by the ordered phase. So if you disorder it, if you melt it, then you have a normal liquid, and then you can make perhaps only a normal colloidal crystal. I don't know.
Because the interaction energy is so strong, so as soon as you put it back down in the nematic phase, the force is so strong that it will bring the crystal.
But there, you see, there are many. What I have shown is this is all directed assembly, right? It's not spontaneous. So if you do this in a real experiment and then heat it into isotropic, then you will see it just collapses into the structure which is shown on the first slide. This is just a more or less random structure. Not completely random. You find regions where this is where this is organized, but not so nicely organized that you could use it. Right?
The spheres are, what is the sphere?
It's silica, but you can work with water as well. We are doing experiments also with water, and it works. You should have some object which has a certain surface boundary condition. It doesn't matter what is it made of, right? You can use titanium dioxide or whatever. It's only the surface properties which are important, right? Nothing else.
More questions? Yep.
I know this isn't a simple question, but what happens if your surface conditions on the particle are homeotropic alignment?
So these are homeotropic alignment.
Oh, so the particles
Yeah.
on the surface
Are at the surface. At the surface of the cell, what?
on the particle itself.
It's homeotropic.
Oh.
Yeah. This was only
What
the.
happens parallel?
If it's parallel, this has also been analyzed. Ivan Smalyukh has worked, and Oleg was working on this.
Is it similar?
It's similar, yeah, it's similar. Basically, you have defects, and these defects again produce the elastic deformation, and this is then responsible for assembly. It's different result, but the principle is the same.
So if we have time for another question, if the next speaker can set up their computer while we ask the next question, that would be great. Other question? Yeah, in the back.
So you showed this collection of two particles being merged. So
Yeah.
you showed these pictures of collections of particles that get raised and so the same
I did not hear it.
Speak up.
So the raised, when you talk about so you had two particles, you had one figure 8 deformation,
Yeah.
and then you would have a third.
Yeah.
And I forget, did you get two? You get two.
It depends. In a planar cell, you always have linear objects, right? In a planar cell. And you make chains or wires, whatever. We call them wires because in some of these structures, the surfaces are very, very close together. And you can think of transporting lights through this as wires. Now they are always along the rubbing direction of the nematic primary direction. Now and there is no two-dimensional, that the single line would run perpendicular to the nematic.